Okay, students, come back and we discuss about welcome back and discuss about the energy bands in materials, why these bands are formed and why certain bands are allowed, certain bands are not allowed, right. This is what we discussed in the last half an hour or so, and using the periodic potential of a crystal and motion of electrons in a periodic potential. So, we have seen that certain energy levels are allowed, certain energy levels are not allowed. That is the reason why band gaps form. So, now not only that, even within each band you can have also sub bands possible. Why? Because of the split of the bands. Let us talk about 2s electron. This is adapted from Callister and Rethwich recent version. As you clearly see that if you consider 1s and 2s electrons, even within 1s electrons you can have sub bands possible, and that is primarily because of the different locations of the energy levels in the Ek diagram, and for each of these bands this kind of sub bands are allowed, and therefore, you create bands, and within band you can create sub bands, and electronic energy can move from one sub band to other sub band very easily. That gives a lot of flexibility for the metals. They can absorb energy and move to the next higher bands very easily, which is not possible for semiconductors or insulators. They need certain specific energy levels to jump from valence band to conduction band. Here it is not required. That is the advantage of that. And many cases bands overlap, like here you can see these two bands are overlapping each other, but here it is not overlapping. So, therefore, depending on the type of band present and whether they overlap or not, the energy electrons can move from one energy level to other levels easily. Well, that is about the electrical property. Let us talk about magnetic property a little bit. Okay. Magnets are widely used. I am talking about various parameters here, mostly focusing on that, so that you know these are the features for in machine learning or deep learning models, and do not take away more than that. So, you know, magnetic materials are very common in our life. We use lot of magnets in our life, whether you were using transformer cores or you are using hard disks. It is basically a magnet. But do you know that magnets also exist in naturally available materials or naturally living materials, like magnetoctic bacteria? They contain a chain of magnetic crystals, nanometric level 35 to 120 nanometers, and we know 1 nanometer is 10 to the power minus 9 meter, right. Very tiny crystals present in this, and why they have these crystals? They are capable of orienting themselves along the earth magnetic field. Imagine, earth magnetic field is so weak, still these bacteria can actually align themselves with the earth magnetic field, along the earth magnetic field, and move. And this is one bacteria, you can see these are the dots, these are magnets, and here I show everything. So, this kind of picture is easily available in the books of Michael Ashby and others, and you can look through it. So, you might be thinking, why not take these small magnets and use it for applications? That is not easy. Okay. They are very small magnets, and they are properly oriented, properly separate crystals. You can see they have nice orientation and nice shapes, and this is done by the living bacteria. It is a very interesting example how they use these magnets to align themselves. So, now the question is this: what is a magnetic material, do you think? Well, you know that if I take a solenoid is nothing but a coil, right, and apply current through it. Because of the passage of current, it will create its own magnetic field, that you all know very well, and this magnetic field will be considered as a flux. The flux lines, number of flux lines or the diameter of the flux line depends upon the distance between the coils and number of coils, that we all know. So, this is basically how the magnetic fields are produced, but there are a lot of naturally available magnets which can create magnetic field without application of any current, right, like pure iron and magnetite, Ap3O4, iron, nickel, cobalt, they are strong magnets. And now, this magnetic thing is magnetic property is explained in terms of the magnetization or saturation magnetization. Magnetization is very easy to understand. It is the amount of magnetic or strength of magnetic material, that is what is called as a in a layman language is magnetic saturation or magnetization. If you increase temperature, material will slowly lose this magnetization, and at a certain temperature, what is called a Curie temperature, at which it will lose completely. So, over this temperature it will not have any magnetization, and that is what is called a Curie temperature or Tc. Tc is very important for any application of a magnet. Tc should be as high as possible, then the magnet can be used at a high temperature, but most of the magnets Tc's are very close to room temperature. So, that is why you need to make new magnets which can operate at a high temperature, and many applications requires that. So, this is taken from again Michael Aspie's books on nanomaterials and nanotechnologies and design. Now, if I have a magnet, how do I measure its magnetic strength? So, what you do is very simple. I take the magnet or I take the material, apply magnetic field, correct. As you know, magnetic field can be applied by a solenoid. What I shown you in this slide, you can put the magnet inside this and apply magnetic field. Magnetic field can be changed by the application of amount of current passing through this coil, also by number of turns. Let us say you are not changing the number of turns of the coil, but you are changing only the current. So, magnetic field will increase. So, as the magnetic field increases, this is the dotted curve you see, we are following lightly that. As the magnetic field increases, saturation magnetization is increasing. You are able to induce magnetization, material will slowly become magnetic. That is what happens when you apply magnetic field, and it will increase, and finally it will reach a saturation value or saturated value. That is what is called saturation magnetization, or the highest possible magnetization value when you apply field. If you keep on increase the magnetic field, beyond that nothing is going to change. Now, let us say you reverse the magnetic field. Reverse means what? It was north south, initially north pole south pole, it becomes south pole north pole, opposite. So, if you reverse the magnetic field, again the magnetization will follow saturation. Basically, you have reached the highest value of magnetic field, then you are reducing in the opposite direction. You can clearly see, then even zero magnetic field, it will also have certain magnetic magnetization. This A stands for 0, right. When you are reversing, you are coming from positive value, you will reach a negative 0, then it will go to negative, right. This one is called remnant magnetization. This is the magnetization which remain in the material even after you remove the magnetic field. You magnetize it, now you are removing the magnetic field. Some amount of magnetization will remain in the sample or material, that is what is called remnant magnetization. Now, if you again decrease the magnetic or go to negative magnetic field, you can clearly see it will go down like this, and then at a certain value of field, magnetic field, magnetization will become 0. That is what is the thing, point D, right. Point D corresponds to 0 magnetization when the field has reached a certain value, and this is called a cohesive field, the field at which the magnetization can be made 0. Then you can still go down and reach again saturation magnetization in opposite directions and come back. So, this is the way magnets are tested, whether soft or hard does not matter, okay. Both the magnets are tested. By the way, soft magnets normally define one in which this loop or this is called a hysteresis loop actually. Hysteresis loop, you all must have read about it. This loop is very thin and very long for the soft magnetic materials. For hard magnetic material, this loop is bigger and larger. So, that is why all the hard magnets like iron, cobalt, nickel, or even your neodymium iron boron, which is used in your speakers, which you use in your headphone, or hard disk magnets, they are all hard magnets. They need to be having a very high the BH loop. This is called H, this is called this is MH loop, very high MH loop should be there. So, that is the typical characteristic of any magnetic material. Remember these parameters. This is the cohesive field, this is the remnant magnetization, this is the saturated magnetization. This is the magnetic field applied, this is the magnetization produced. These parameters are important for you. If you want to design a new magnet, let us say hard magnet, which has a higher saturation magnetization, lower cohesive field, you should know what is what, right. That is why this picture should be very clear in your mind when you want to design something using machine learning or deep learning models. Now, what actually happens atomistically? Why this curve is like this? Well, atomistically magnetization is because of electron spins. Electrons have spins actually, it can have up spin and down spin, they are all particles. So, when they move around a nucleus, depending on the spin, if the spins are aligned opposite direction, like here one is up, one is down, then you have a 0 net moment. So, therefore, there is no magnetization. But if in the second case B, there is one electron which is spinning up, there is no electron opposite to this which is spinning down. So, there is one electron magneton, but this is called Bohr magneton, because Bohr was a scientist, that is by his name it is called Bohr magneton. Now, if I add another electron here in the opposite spin direction, there is no net moment. This is the reason for magnetism. In atomistically, this is what happens. So, now in a real material you have large number of electrons, correct. Depending on the spins, how they are oriented, you can have 4 different types of magnetic materials. First one is called paramagnetic. In case of paramagnetic, everything is random, electron spins are random, so they do not add up anything. It may have a weak magnetization, very weak, which is not of any useful thing to us. Oxygen is paramagnetic, pure oxygen is a paramagnetic field, but if you apply huge magnetic field, it might behave, it might produce some amount of magnetization. That is what is done in case of many of these magnetic resonance imaging array, MRI, what is known as MRI in medical technology. They use a magnetic field to align the oxygen atoms in the brain or in the various cells to know what is happening. Now, second type of magnetic material is called ferromagnetic material, which is called C. In C, you see everything is aligned perfectly in a certain direction or the direction of the field. That is why they add up and give a huge strength. Iron is a ferromagnetic material, cobalt is also, nickel is also, Fe3O4 is also ferromagnetic material, but it is a very rarely seen, very this kind of elements are very rare. What you can have is a variation of these elements. Here you see on the B, you see some are positive, some are negative. That is called antiferromagnetic materials. Okay. But whatever it is, it gives you some magnetic moments or magnetization. Last one is called ferrimagnetic, in which there is opposite and poles, opposite spins, but values of the magnitude of the spins are different for the up and down. So, this gives you some magnetic moment, right. That is what happens in a ferrimagnetic material. So, this is what is the classes of magnetic material possible depending on the spin. Now, there is another important thing you have to understand. When you apply magnetic flux or magnetic field, the spins will align along the magnetic field. That is what is shown here by the arrow on the left side. This is again taken from Michael Asby's books. But if you have a large material, the spins may not align always in certain directions, or it may undergo the reversal of directions. So, when it happens, you create a boundary between the spin reversals, that is called a domain boundary. So, each one is a domain, okay, these two, and this is a domain wall. That is the wall which is differentiating between that. So, when the spins will change, rotate, they will rotate slowly like this. So, that is what rotation will happen and spin will go to the other one. So, domain walls actually takes a lot of energy. Now, real magnetic materials like this one, you see there are different element of spins possible. So, here you have different domain wall possible. Same thing has shown here also on the bottom side, picture C and D. You can see that different domains are there and each domain is differentiated by other one by domain walls. So, this domain structure is very prevalent in the magnetic materials, and that is what sometime we need to know, because all the properties of whatever I discussed will depends upon this size of domain wall, size of the domain, many things. So, when you make materials to very small size, nanometric size, lot of new things can happen, new physics can come up. Let us talk about a little bit about that. So, as you clearly see, this is this MH curve or BH curve. There is a B here, B is basically flux, M is the magnetization, but shape of the curve looks same. So, if I take any material, start reducing the size of the grains, what will happen? Initially, it will have some values of magnetization. Basically, this is we are plotting as a coercivity, this is the one we are plotting, but it can be magnetization also. And then after below a certain value of grain size, magnetization will increase tremendously, very high value magnetization. It is called superparamagnetism. So, it is called superparamagnetism. Magnetization will increase tremendously. That is because all the domains which are there, they will be single, every grain will be a domain. So, you have small grain like this, and each grain has a single domain, and each domain is each spin is aligned in a particular directions. That gives a huge strength. So, therefore, magnetization increases extensively. But if you decrease size further, thermal effect comes into picture, because at a finite temperature you have a thermal energy, and thermal energy is basically kT or 3 by 2 kT. Thermal energy K is the Boltzmann constant. Thermal energy will try to destroy these spin arrangements or spin arrangement or alignment, and again below certain gain size thermal energy will take over the magnetic energy, and then the magnetization of the quasi field will decrease very low value. So, there are two values, one is the d critical, one is the d sp, and sp stands for super paramagnetism. That means below certain gain size any material will become paramagnetic, and that is what has been observed in all the nanomaterials, many of the nanomaterials, which is very typical of nanomaterials. So, in a nutshell, if you want to have a strong magnet, you should work in this regime, right, in the regime of the gain size, which is very important. Otherwise, you will have lower magnetic strength or magnetizations. That is what is important. So, some of the magnets like neodymium iron boron, I told you, right, which is widely used, or samarium cobalt, these are rare earth magnets. These are widely used various applications. They realizes these concepts. So, gain size is controlled in such way that you can achieve certain level of magnetization, and this is reflected by this plot. So, therefore, these are the important features of electrical properties or magnetic properties which you should remember. And if you want to go through much detail of these, please go read the books which I am referring below many of the slides. Like here I referred this book of Michael Ashby, Daniel and Paulo Ferreira. So, it is easily available, one can buy it or one can get it from online stores. So, you need to read these aspects, because some of you may design magnetic materials, some of you design electrical materials, some of you design structural material, some of you design something else. So, you should know these properties of this material, what is important. You want to design a strong hard magnets, what are the properties you need to consider, what are the things you need to consider. Obviously, you need to consider larger BH, a larger MH area, right. So, what are the things important here to get that, whether you need a high value of coercivity, high value of remnant magnetizations, high value of saturated magnetizations or not. Or if you want to design a material which is used for magnetic switching, there you need to have a very small small area long MH curve. How to get that? What kind of materials will show this? How to design those materials? How to know their compositions? How to understand that these materials will be useful for any industrial applications? So, these are things one can do. So, you understand that doing experiments is going to take a longer time to discover new materials. Rather, we can actually design the new material using this statistics or data available in front of us, and using ML model we can design these materials very easily. Okay, so, let me stop here. We will come back to you with other properties of material and material processing aspects in the next couple of lectures. Then we will jump into the statistical tools and the machine learning tools. Thank you.